Am I sharing the right screen? Are you guys? Oh, no, I'm not. Let's do this again. I want screen two. I want to share that. Okay. You guys see PowerPoint before I get this going?
Yep.
And disable captioning. There you go. So, starting off the night, welcome everyone. I got a pretty large group tonight with 14 people. That's quite a bonus. So tonight is the monthly meeting for the astronomy fundamentals group here with the Tucson Astronomy. I am Connor Justice, and we'll be having two presentations tonight. The first one, as the one I am about to give, is on astronomer Maria Mitchell. We'll learn all about her in the next 20, 30 minutes before handing that off over to Stephen Ferris for what I had given his record in the past will be a very interesting presentation on the James Webb Telescope, as well as infrared astronomy. Stephen, if I got both of those topics correct. If you had anything else you want to add?
We're just going to stick with James Webb tonight.
James Webb, okay. I know that you had preparing both, and I know James Webb does infrared, so I was kind of blurring you together. So, okay, so just James Webb then, but that nonetheless should still be an interesting presentation. And while Zoom keeps up in my way. So starting off with Maria Mitchell, quite notable in terms of women in astronomy. She was born on August 1st, please excuse the typo in there, in 1818 in Nantucket, Massachusetts, to a Quaker father and mother. She was the third of 10 children to to this family, so a very large family group. And because one of the cultural aspects of Quakers is that all the children are taught equally, she received the same education as all other children in her family, boys and girls. So she was quite privileged for that in this particular period in history. Her father was the principal of a local school, which we'll talk more about that here in a second. And her mother worked in the local library, off and on as more of a clerk, an account and record keeper. And on the right here is a picture of Maria Mitchell, I think around the age of her late of her 50s. But we'll get to more about that. So as part of her early childhood, with her benefit of her father being a school principal, she was able to actually enroll in the school, which was also atypical of the time period where it was a mixed gender school where it taught both boys and girls. She was primarily taught in the school math, astronomy, and science. And by several accounts of her during this period, she was very gifted in math. The other benefit of her father is that her father was also a very avid amateur astronomer and helped operate the local observatory for some of the whaling expeditions that would go out of Nantucket. And outside of class with her father's background, he heavily encouraged her to help learn navigation and surveying, which will come in later briefly for a portion of her career. As I mentioned, she was apparently very gifted. At age 12, she would assist her father with calculating the position of their home by observing a solar eclipse. And I'm more interested to see how many people of us would want to take that on as a challenge for the April total solar eclipse next year. Maybe a little bit too soon to try to learn that math between now and next month. By the time she was 14 years old, the local captains of ships sailing in and out of Nantucket would take their ship's clock pieces, which they used in order to accurately navigate their ships across the ocean, would take them to her in order for her to calibrate and repair them. And she was widely respected for her skills in this particular regard. And so the fact that you have many captains trusting a 14-year-old to calibrate what is a very sensitive clock speaks to her abilities overall. And by the time she was 16, she herself opened a mixed race schools for teaching young girls math and science. So she's very, very gifted at this early age. We skipping over a good chunk. Unfortunately, during the process, we don't really know much more about her between this early period and by the time she makes her one of her first discoveries. It is believed that she destroyed most of her early correspondences and letters, in part because during a fire in Nantucket, which burned down parts of the city, she had witnessed many writings and letters and other private correspondence she's just whispering about. And so there's a suspicion that she was terrified of a second fire and having her personal life exposed for all to see through letters that were never recovered. So to avoid that, she destroyed a lot of this early correspondence. So we're skipping over quite a bit of time in her life. So her first major documented contribution to astronomy was in 1847, where she discovered the comet C 1847 T1, which would later be named in her honor as Miss Mitchell's comet. She found this comet using what a 3-inch refractor, and I'm the picture on the right, obviously being excuse me, a a a post rendering is probably not the telescope that she used for this activity. I think I saw that it was out of the observatory with her father that this discovery was used, so that she was using at the time. As part of this, though, she was able to get an award from King Christian VIII of Denmark, who had set aside a lot of money to award to discoverers of of telescopic comets, that is, comets that you could not see without the aid of a telescope. So this was kind of an incentive prize by the King of Denmark to encourage this activity. So although it was an award, it wasn't necessarily it was more of a general award, not necessarily something specific towards women or for any of her own for any merit upon herself, which is unfortunate. She sorry. The only previous woman to discover a comet before her were the astronomers Carolyn Herschel and Maria Kirch. That's not on my slide because I ran out of room. And this gold medal was also the first award given to a woman in astronomy. So a lot of firsts so far with her. We're not even a third of the way through the presentation. She also, in addition to this, became the first woman elected, like 6 months later, to the American Academy of Arts and Science. So lots of prestige heaped on her really quickly in a very short time. Although she was awarded this gold medal, she didn't actually receive it till about 2 years later. So they're kind of, so it's hard to get things over the Atlantic Ocean in the 1850s. Shortly after this, as her next move in her career, she accepted a position with the U.S. Coast Guard at their Almanac office, where she would go on to help assemble navigation tables for ships here within the U.S., primarily being concerned during this time with the planetary movements, notably Venus, to help assist in this record. About a year after that, she was then elected to another association. This time, she was elected to the American Association for the Advancement of Science. So she's a social butterfly, just getting all over the place here. And she would spend her time there at the Coast Guard for a couple more years. And by the 1850s, mid 1850s, she took off and started traveling around Europe, and would go on to meet a lot of other European astronomers, including Carolyn Herschel and Mary Somerville. Actually, I don't think we've done a presentation on Mary Somerville yet, but Carolyn Herschel, we have done a presentation on her and most of the other Herschel family at this point. So both people, very big names in this time period. So she's, this what today would be like an unknown American woman just meeting a whole bunch of really famous scientists, so getting around quite a lot. Skipping over her activities during the Civil War, mostly of that was rated during her time period was related to her assistance with assisting escaped slaves from the South, and which is important, but to keep it focused more on her scientific contributions, I'll be skipping over that particular time period. Um, but despite her never attending college, she only had this initial education from her father in the schools around in Nantucket. She was recruited as a professor to Vassar College in 1865 and became the first female professional astronomer in the U.S. What was interesting is that it was also noted that her tenure on the staff was a key contributor in allowing Vassar College to recruit more people than Harvard to their math and astronomy courses. Her name by this period is carrying a surprising amount of weight given the time period and what you wouldn't normally have associated during the 1800s. This job came with a lot of perks. Being the head of the astronomy department, she was also the director of the observatory at Vassar College, which allowed her exclusive access to a 12-inch refractor, which I believe is this one here on the right, which at the time was the third largest telescope in the US. So she is just, it still is like there's more to this than I could have put. I just ran out of time. There's a lot to her, and I definitely encourage people to go look more of her. Continuing with her time here at Vassar College, her primary research was all over the place. She made minor contributions in the study of nebula / galaxies. Just keeping in mind that during this time period, science we hadn't officially separated nebula and galaxies as two distinct objects, which that separation wouldn't happen until Hubble in the 1940s. So it's unclear from the way the articles were written if she was looking at nebula only or if she was also looking at galaxies, given their combined naming during this period. But her biggest contributions became in the contribution for solar astronomy. She was the one of the first astronomers to begin active daily photography of the sun and sunspots, which which contributed to her making the discovery that sunspots were not actually clouds on the sun; they were actually cavities on its surface, which was a pretty big deal at this time. Also, one of the things that she did is she would actively encourage her female students to attend observing sessions and nights in the observatory, which was against a lot of cultural norms during this period. From not exactly sure why they were particularly frowned upon, but there was just this distinction that they didn't generally like women out at night. I might have been for a safety thing that or during this period, especially it's shortly after the Civil War, 1865 to 1870. There's kind of a lot going on socially here in the U.S. Given her position, she was actually also the most prominent member of Vassar College in terms of faculty, but she suffered what we now know today as a huge pay disparity between her and the male teachers at the college. She and another professor, Alida Avery, who was a key member of the college's medical department, were conveniently able to actually get that addressed pretty quickly, though, once they found out the issue and the college was insufficiently raised their pay. So that was good to see an interesting and positive response from the university there. And as I mentioned, she did had her astronomy interest covering a variety of topics. She was, by many accounts, a very skilled educator and very influential. And 25 of her students would later go on to find their name in the Who's Who in America list. 2 or 3 of her students would go on to make the list of the counterintuitively named Academic Men of Science in 1906. Both 2 of the women were mathematicians by their trade. They were Charlotte Scott and Grace Andrews. I say it may have been third. One article I saw quoted 3, but didn't name them. But when I went to go look at the list for who was in this first issue, only two women were mentioned. So I'm not sure if one of the sources was wrong, which I was looking at. Um, and progressing through her career, she would also go on to found the Association for the Advancement of Women in 1873 and would become its first president in 1875. All of this while managing her duties at Vassar College. I think this is on the right is another picture of her at Vassar Observatory using that 12-inch refractor. She would spend the rest of her life as a teacher at Vassar College, retiring in 1888, where she would go on, and after retirement, she would go return to Nantucket to live with one of her sisters until her death in 1889, where she died of brain disease. Her home has since been turned into a museum, and it is open for visitors from what I was able to find. So if you do find yourself in Nantucket, and like astronomy places, and astronomy history, definitely might be one of the more interesting places to stop by if you do find yourself there. The telescope that she used at Vassar College is now part of the Museum of American History's collection. I'm not quite sure. The Smithsonian's collections are quite large, and so they cycle them throughout the museums. So I'm not quite sure if this telescope is one that's currently on display in the museum or part of their backlog collection, which they keep in the back rooms. And lastly, more recently, she has been given her own lunar crater, which aptly named Maria after her. So this might be a little bit hard to see, but this big crater here, let me turn on my laser pointer. So this big crater here is the Aristoteles crater. And I'm not quite sure which orientation of the moon, if this is closer to the north face or the south face of the moon. But if you search for Aristoteles crater on a larger image, that'll help orient you. Her crater is this small one that's kind of hanging here off to the right. If you can see that just above the red laser pointer. And that wraps up Maria Mitchell. Definitely a lot to her and a lot more that I could put into in this short presentation. Definitely was cool learning about her. Any questions or comments before we move on? Okay. I'll take that as a no.
Well done.
Stephen.
Thank you, Connor.
Thanks, Pete. Stephen, I guess we'll jump over to you now for what I assume everyone else came for. It was not listening to me talk about Maria Mitchell, but talk about the giant fancy space telescope that took 20 years to get into orbit.
You need to let me screen share.
Oh, you left it after I made you a co-host. Sorry, let me do that. There you go. Try that now.
Let's see what we got. Looks like it's working. Give me just a second to switch over. Oh, where my cursor go? And we're gonna go James Webb. All right. So James Webb is a little bit of a challenge to try and present on because, as Connor alluded to, it's only been in space for about 2.5 years, but it was a 25-year journey for a lot of people involved to get there. And as several of you who know me well know, up until about 3 years ago, I would have said this thing was going to end up in the Smithsonian and never fly. That said, it has become one of the most important cosmological and astronomical missions in NASA history. Very quickly upon reaching orbit and reaching full operating capacity. There's a very long history that if anybody wants to go into in terms of the many different uh, ways in which this project almost didn't happen, going back to 1996 when it was first proposed along with another potential space telescope. There was a time in 2011 where it almost looked like it was going to be canceled. It is, up until the time of its launch, fairly controversial in that it ate up a lot of money for other astronomical projects that might have happened without it. But that said, and the politicians behind NASA kept it going for the time that it would took to get to orbit, and now we're bearing the fruits of it. So rather than go through a lot of the kind of long history, I just wanted to look at the positive side of this, which is the more recent things that have happened with this particular project now that it is such a tremendous success, having reached its orbit and having unfolded properly and now functioning almost perfectly, in some ways better than it was originally expected. So it's a very exciting project now that it's happened. In some ways, it's sort of the Apollo program of the modern age. It certainly has, yeah, for those of us who are into the astronomy side of NASA rather than necessarily the manned spaceflight side of NASA, been pretty exciting. The other thing I wanted to do with this particular presentation very briefly is to kind of inspire folks to think about missions, because uh, we've done a few missions as part of AFSIG over the years, and I'd love to start a tradition of maybe doing that as a series with other people involved. There have been dozens of missions. The ones I'm interested in are mostly unmanned because in many ways, the unmanned missions, with the exception of Apollo, probably have had as big or a bigger impact on science than some of the manned missions. That's not to say there weren't areas where the space shuttle was important to science and the like, but for in terms of planetary science and in terms of astronomy, um, the missions of the unmanned missions put up by NASA have been absolutely phenomenally successful. And this instance is the one that is sort of getting the attention right now. I thought this would be a great place to start that. So, James Webb Telescope basic facts. I'm not going to have a lot of lists of information tonight. It's mostly going to be pictures that I'll narrate as we go along. But I did want to kind of present some basic information. It was overseen by the space and still is overseen by the Space Telescope Science Institute on behalf of NASA, as well as ESA and the Canadian Space Agency. The primary contractors were Northrop Grumman, which built the overall spacecraft, Ball Aerospace, which I believe was primarily responsible for the mirror and some of the other technology. And L3 Harris, I can't see around my picture, but it was a lesser contractor. The actual launch date was December 25th, 2021. So it's kind of a Christmas present for the planet 2 years ago. It entered service officially on July 12th, 2022. The cost is approximately $10 billion. So to put that into some perspective, the latest aircraft carrier that has been built and is now operating, I believe it's the Gerald Ford, is approximately 13 to 14 billion dollars. So we're on the same kind of cost as that. I personally, being an astronomy fan, would pay for the space telescope before I pay for the aircraft carrier. But if you're into that kind of thing, we got both. The cost has been pretty significant. The project began as the Next Generation Space Telescope in 1996. To put that perspective, that was 25 years ago. It was actually, it's not 26 years ago. The original budget was about $1 billion in the money of the day. Obviously that kind of just summarizes how much the costs overrun. Yes, there's been inflation and things like that too, but the original plan launch date was actually 2007 when the Next Generation Space Telescope was first proposed. It didn't happen until 2021, so there was obviously some major delays throughout the project. The construction of the main telescope was completed in 2016. The remaining 5 years was for testing and other little glitches which came up, but mostly to make sure that the thing would operate as it was supposed to after this massive investment had been made in it. Some other basic facts: it was launched on an Ariane 5 rocket from Kourou, South America. Ariane was one of the Europeans' main contributions to the project. In exchange, they get a certain amount of time on the telescope, along with another instrument that we'll talk about briefly. The meter diameter of the mirror is 6.5 meters. And to put that in perspective, we've had several presentations I gave on large telescopes. This is comparable to the Magellan telescopes, the small, well, they're now small. They're originally very large, single mirror Magellan telescopes in South America, or the LBT, not the LBT, the uh, MMT up on Mount Hopkins. The focal ratio is f20, so it does have a very slow focal ratio for our telescopes. It's probably not that short, long of a focal length for professional telescopes, but for the ones that we use in the amateurs, that would be considered fairly long focal length. Collecting area is 25.4 square meters. It has a very unusual optical design called Quarsh. As far as I can tell, that simply indicates that there are three different mirrors, which there's the primary and the secondary, and then behind the primary, there's another mirror which then bounces it back to the instruments and basically provides fine guidance to the imaging. Um, and the dimensions are of the telescope overall, the entire spacecraft are 21.2 meters by 14.2 meters, um, which is about 60 feet across. The mass is 6,500 kilograms. Interestingly, that mass is approximately half of what Hubble weighs. There are a number of reasons why it had to be so light. The biggest is it had to go out to Lagrange point, I believe it's 2, whereas Hubble can just be shipped up there in orbit. It has to be a little bit lighter to get there, although it is a much larger object. The mirror composition is beryllium, and the coatings are gold. It's a very thin plate of gold, and certainly not the most expensive part of the telescope. The reason for a gold mirror is, of course, it tends to reflect a little bit better in the infrared, which is the main focus of this particular telescope. And I do need to emphasize, just to begin with, this was always conceived of as a infrared telescope. So it can barely see into the very reddest part of the visible spectrum, but it was always designed as a infrared telescope. And I'll come back to the significance of that in just a bit. Unlike Hubble, which is meant primarily for optical, but can also see into the UV and a little bit into the infrared as well. And that was why the designing of it was built around what the needs for infrared. Um, One of the needs for infrared is that your instrumentation, at least, is cold, because in warm temperatures, if you're an object that is warm, you're going to be emitting in the infrared, especially in the mid-infrared, which would create a glow that would sort of overwhelm the instruments. And this was, again, always conceived of as being an infrared telescope. So they had to come up with a lot of very innovative and very complicated technologies to make that work. One of which is that massive sun shield that you see towards the bottom in gray in this particular diagram. Obviously, the mirror and the telescope assembly is pretty cool, but it's the sun shield that provides the passive cooling for the instrument. And it is something that blocks the sun and more certainly the thermal radiation from the sun and allows it to cool to the telescope assembly to cool to very low temperatures. There's also the main mirror, which we'll talk about in a minute, the secondary mirror, and then the assembly behind it, which is where the instruments are held. All at very low ambient temperatures, is protected by the sun shield. And then there's the bus, which is that box down towards the bottom. That is the primary spacecraft, which contains things like fuel and the thrusters and stuff like along those lines. Those are on the warm side. And then there's a solar panel that's very hard to see on this, that provides the power for the telescope. This
Yeah,
is
it's
another
actually
look from the side.
it's actually about
Go
that. Is
ahead.
that what the telescope was powered by? Because in pictures I've never seen it with solar panels, so it was like,
Well, it does have a solar panel. They don't emphasize that much, but it is obviously on the warm side because the cold side is blocked from the sun, but it is solar powered. I don't think NASA was interested in creating a nuclear battery for it. So it is solar powered, but you never see that in the diagrams. This is what it looks like from edge on. And as you can see, I'm sorry. The instrument The instruments are in. I don't have a pointer with me, but you can make out where the primary mirror is and where the instruments are behind it, and then of course where the massive sun shield is. That provides most of the length of um, the telescope. This is a look at the spectrum that these different telescopes are looking at. And Hubble, as you can see, is primarily looking at the visible, but it does go into the ultraviolet and slightly into the infrared. Webb is primarily focused on the infrared, namely the near infrared and the mid infrared. The Spitzer Space Telescope, which is an older telescope that has since been decommissioned, could see further into the far infrared than Webb could, but it obviously did not have the aperture that Webb has, and therefore doesn't necessarily. It's a somewhat different mission in terms of what it was focused on. But again, Webb was always conceived from the beginning to be primarily an infrared instrument. This is a little bit blurry of an image. This is the diagram of the assembly that holds the instruments. There are four instruments on Webb, three primary instruments, and one which is primarily a guidance sensor, but also contains a spectrograph. Three that I'll focus on are NearCam, which is the near infrared camera built primarily at the University of Arizona and is able to do imaging at the near infrared wavelengths. There's Near Spec, which is built as a collaboration that also include members at the University of Arizona, but it was a wider collaboration that provides the main spectrograph for the near infrared. And then there's MIRI, which is the mid infrared instrument, is both a spectrograph and a a camera with that can view into the mid infrared. And it is primarily a European project. And although there are obviously all these instruments have international collaborations and parts were made all over the world, it is the other main contribution of ESA. FGS was built by the Canadian Space Agency in exchange for, again, time on the telescope. Um, so again, this is how the telescope is cooled. So if any of you are familiar with Spitzer or would want to do a presentation on Spitzer, it was primarily, it was a smaller telescope, smaller than Hubble, but it was primarily actively cooled, meaning that it was contained within a dewar containing liquid helium, obviously at very, very low temperatures. Webb uses a very different kind of technology. MIRI is actively cooled to a certain extent, but most of the telescope, including the main optics, are cooled passively with this massive sun shield, which blocks the sunlight and the thermal energy from the sun and causes it to the main telescope and the instruments to cool down to very low temperatures, up to 233 degrees Celsius. And that allows the telescope to cool itself without needing a lot of extra material like liquid helium, which not only makes it a simpler technology overall, also lengthens the potential life of the telescope because it is limited more by its fuel supply and its ability to stay on orbit than it is by limits like the amount of helium on board, especially for the near infrared instruments. And as you can see, there's the solar panel. Finally, you have a picture of that on Edge On. The main computer is contained in the bus, and the steering is also in where the bus is. Most of the steering is done by reaction wheels, just like it is on Hubble. The thrusters are mostly station keeping, with keeping it on its particular orbital point. This is a cross section of what the heat shield looks like. There are 5 layers. I believe they're what is it, Kevlar or Mylar? I'm probably getting that wrong, but they are coated in doped silicon. And I had to go look what that means. It's basically a electrical term, but it provides a reflection of both the sunlight and the thermal heat back out into space, which is allowed to cools. If there had been any problem with deploying this thing, the mission would have failed. This was one of the areas where the critical failure points would have come in. Fortunately, and they did have trouble on the ground getting this thing to unfold, but it worked perfectly, and it is working perfectly, and it has cooled the telescope to the temperatures that they're looking for. This is a picture of what it looks like unfolded. This is actually a test unit, not the one that was actually used in the telescope itself, but it's still the same basic technology. You can get a sense of what this looks like. A very big, not as big as a football field, but it is a big piece of very, very, very thin material. This stuff is about the width or a little bit less than the width of a human hair. And it's quite thin, obviously, to save weight. The primary mirror is, again, Hubble is about a 2.5, 2.6 meter mirror. This is a 6.5 meter mirror. You'll notice that it's a compound hexagonal mirrors like exists on Keck. We talked about that in a previous presentation, how that particular technology works. Keck's mirrors are, of course, glass with usually silver coatings, whereas this is beryllium metal with gold plates. Again, the reason for the gold plating is to maximize the reflection in infrared. And the reason why that is, of course, just like with Keck, it creates a lighter mirror, which makes it easier to put into space. But also, we don't have a launcher currently with a 6.5 meter diameter fairing. So, as I'll get to in a minute, you had to fold this thing up to put it on an Ariane. So the best way to do that is a compound mirror that can be essentially moved into parts and then folded and unfolded once it gets into space. This is an idea of what the optics look like. Again, there's an additional tertiary mirror that provides fine steering to the telescope, and then the primary and the secondary are just like with any other Cassegrain style telescope. Um, Another diagram kind of showing how this breaks down. Up in the front, you have the secondary mirror and the aft optic subsystem and the primary mirror with its component parts. The framework that you see is to hold the mirror components into place. There is a simple system, somewhat like an active optics system on this, but unlike an active optics system on the ground, which has to constantly reshape the mirror to accommodate with gravity. There's, essentially very little gravity effect on it in space, and that's a whole nother lecture and how that works. But there is gravity acting on it, obviously, but it's in an orbit where it doesn't necessarily the mirrors are not going to warp much. So it only has to adapt occasionally to maintain fine focus, unlike the active optics system on a ground-based telescope. And the thermal management subsystem is primarily for MIRI to keep it colder than the rest of the telescope. Let's see, why did that happen? Uh, uh, so where did the rest of the presentation go? Let me see if I can recover that.
Gonna pause the recording real quick while we sort through this. Cool. Glad we were able to
Right.
recover. Thanks, Steve.
Okay. And I don't want to go from that. I want to go to current slide. Okay, so again, this is what it looks like fully deployed, and there's the sun, the solar panels, and you get a general idea what that looks like. So this is a picture of the mirror fully unfolded with the secondary mirror folded against it. Obviously, this is on the ground, not in space. You can see the technicians working on it. This thing was folded and unfolded several times on the ground to test to make sure that it would operate properly. And so there's a lot of different phases of its operation that we can look at. This is, of course, an artist's conception. There's no second rocket taking pictures of it on the way up, but this is principally what it was supposed to look like once it was inside the fairing of the Ariane 5. It was essentially as they've called it, an origami project in space, which was designed to fit within the fairing, which is 5 meters for a 6.5 meter telescope. Again, this gives you an idea of what the mirror looked like with that one segment sort of being folded and unfolded in the side. It was unfolded, folded, unfolded, and folded and unfolded until you had it finally prepared for launch. This was probably one of the later times that it was done. Again, there's with a segment now in the folded position and the other segments in the unfolded position. This is what it looked like all packaged up and almost ready to go for launch. It doesn't look like itself, but it's not supposed to. That's in order to get into the fairing. And a couple other pictures of that is they were doing various final testing on it, both in the U.S. and then in Guyana. The most of the testing, of course, happened here. The final assembly or the final how to put this, the telescope was put on the rocket in South America. Everything else was pretty much done here. This is what the unfolding scenario looks like. It comes out of the fairing, and unfortunately, doesn't have a very high resolution. But you can see how the first thing that was unfolded was the heat shield, and then the mirror unfolds, and then finally the secondary is put into place, and it is in its final position. And this is to give an idea of what the L2 orbit looks like, and how to describe, I think everybody has probably familiar with Lagrange points and how that works. It's basically balancing points of between Earth's gravity and the sun's gravity. This one was put further out than Earth because you wanted it facing away from the sun, and also the reason it was put at a Lagrange point and not around orbit was to keep it away from both the heat source of both the Earth and the moon. Because again, anything that's emitting a large amount of infrared radiation could potentially blind or impact the imaging capacity of the telescope. The Earth does not provide a heat shield or a light shield for the telescope. Is obviously the orbit is kind of a halo orbit and it's in full sunlight almost all the time. At least the one side of it is. So that wasn't ever conceived of as being something that would be useful, but it is a way to keep it away from Earth as a heat source and the moon as a heat source. And this is an artist diagram of what it looks like. Obviously, this is greatly exaggerated and made to look pretty, but not really this is essentially what it would sort of look like in space. Another image of that. Again, you can see the shielding laid out with the sun shield, and then the telescope and its optics in full arrangement as it is now. In order to get the optics to work properly, it took several weeks or several months to get everything in proper culmination and alignment. And this was one of the first alignment images. They had a particular star that they had picked out beforehand that they would use for the alignment of the mirrors to get it into proper culmination. It, Webb has a very peculiar arrangement of the diffraction spikes that come off of the images of bright objects and stars. It's a creation of both the secondary mirror framework and the way that the different parts fit together. Typically, it's a cross. There is a nice diagram that's out there on the internet. I didn't want to go too far into depth of why it looks so. It's got 6 spikes with a second cross in the middle, but that all has to do with the way the optics are laid out. It can be used for in solar system planetary science. I couldn't find a lot of good images easily on the web when I put this together. This is Jupiter. It has done some really cool stuff with Neptune as well, and some of the outer planets. This is what an infrared image of Jupiter looks like. You can barely make out the ring. And certainly it looks a little bit different than it does in optical. These are the warm parts versus the cooler parts of the atmosphere. And the rest of this is just to give an idea of what the different pictures look like. So one of the objectives of the telescope was to look at things within our own galaxy in the infrared. This is a planetary nebula at different wavelengths to show what this looks like in comparison. Um, and of course, it creates a lot of pretty pictures too that way. Um, and this is sort of a high resolution image of that. I wasn't able to find a good explanation of which object this is. If anybody knows, you can jump in.
It is the
But
Southern Ring Nebula.
Okay, it's the Southern Ring Nebula. Thank you. This looks at a different wavelength than Hubble does, so it's seeing a different material than Hubble would. It's still the same basic object with the same sort of shape, but it is looking at some of the gas and dust in a very different way than Hubble would. This is the Tarantula Nebula in the Large Magellanic Cloud. And this is, I don't have a comparison picture from Hubble, unfortunately, but again, it's looking at some of the low temperature gas and dust in the nebula. And I believe that this may have some composite parts from old Hubble images in there as well. Unfortunately, that has been sort of the tradition with a lot of the images that have been put out in the public is they've brought in some optical material to make people make a little bit more sense. I need to make a comment here about color, which is that with all the images that we're going to look at that are taken by James Webb, none of these are in color wavelengths that we can actually see. So NASA kind of assigns a color palette based on what looks good and what may be scientifically valid as a way to sort of bring out the life in these images. So again, what you see as red or you see as white or you see as blue is typically not white or red or blue. It's an assigned color at a certain wavelength based on the light bands that are received by the different sensors. So basically, what I'm saying is it's all artificial color. There's no there. If you could see in the infrared, this would be visible, but we can't, and they have to have a way to sort of visualize this. That doesn't mean that the structure is incorrect. It just means that the colors are assigned based on different wavelengths that are not necessarily anything that we would see. This, of course, is the pillars of creation, made famous by Hubble as well. Again, this one of the things that they built an infrared telescope is that the dust tends to be more transparent to infrared light than it is to visible light. And so you can look in and penetrate to a greater depth objects which are covered in dust. And one of the things about that is that when you look at the pillars of creation compared to Hubble, you can see some of the stars that are forming inside the nebulosity and the dust, which is a little bit different from what the Hubble image looks like. It's exactly the same picture. Again, the colors are artificial, but then the Hubble colors are kind of artificial too, but I didn't say that. But the point being there is that you can penetrate some of the gas and dust a little bit better with the infrared than you can with the visible, which creates a different kind of image than you'd have with it. Again, more of those nebulosities that they're looking at. So it's very much meant to look at galactic structures as well. This is extragalactic. This is a fairly new image. It's only come out in the last few months. This is M74, which is a nearby spiral galaxy. And there's lots of images out there of M74 and the visible. This is looking more into the mid and far infrared. The reason this is cool is that it's literally cool, right? It's cold dust and cold gas compared to what we see with some of the optical images And it kind of shows how some of these voids and overdensities exist within spiral galaxies that may not be as visible with the visible light telescopes. You'll notice some of these very large voids, and again, I don't have a pointer that I could point to, but there's different thinking about where those have formed, and one of them, of course, the possibilities may be the results of supernova explosions or other kinds of things which sort of blew out bubbles of gas and dust inside the structure. But overall, the spiral structure becomes very visible within these spiral galaxies as well. What it shows is that spiral galaxies are full of a fair amount of gas and dust, about 8 to 10% by mass, but compared to ellipticals, which have very little, it is something which comes up in the infrared, and we get a little bit idea of what the gas structure is compared to others. This is the whirlpool. Very different kind of image than we get. A very common target for amateurs to photograph, but it is, you can see some of those voids and over densities in this particular structure as well. And again, there may be some visual components added to that, but this is primarily an infrared image. And this is also a comparison of the same objects. I believe it's M74 with the Hubble on the left, Hubble and Webb in the middle, and the pure infrared images on the right. So revealing different information as we go along, depending on what you're looking for. I believe this is Stefan's quintet, again with the visible and the infrared imagery kind of combined. So you can make out some more of that gas and dust than you can with the simply the optical. It is more highlighted and certainly more prominent. This is the famous cartwheel, again with Hubble imagery overlaid with the Webb imagery. Again, those dust bands and nebulosity become very visible in the infrared because they are at cooler temperatures, which the telescope is targeted at. A big part of the focus of the original mission was to do cosmology with this particular telescope. And the large aperture and infrared sensitivities were built in part to do that cosmology. The reason for the interest in that is, of course, the light penetrates the dust, but more importantly, because of gravitational redshift, the universe slowly spreading out, actually not quickly spreading out, but because the universe spreading out, light that was once in the visible and the ultraviolet very early in the universe, which is emitted in those wavelengths, has been stretched out over time into the infrared. And so the interest of the infrared was to look very far back into the past and be able to do cosmology of the early universe this way. There's also an extra trick that certain projects are throwing in, which is to use a gravitational lens to look way back. So the gravity, of course, will bend light and create a lens in space. It works like a very primitive but very large, powerful refractor. And sometimes we combine the infrared capability of the telescope with these large foreground galaxy clusters, and you can see some of the images that come out from even further behind that in the form of gravitational lensing. And this is basically a diagram of how that works. So the lens galaxy images, you can have multiple images of the same galaxy. And oftentimes they're more in the infrared than they are in the visible, and you can get a lot of data that way. This is an example of what one of those looks like. The two arrows point to areas that are lensed. We have to be careful looking at these images because, of course, the lens distorts the original image, but you can see things that normally would be much harder to see in the distance thanks to these lenses. So they may probably looking at the same galaxy image here in from two different parts of the lens. And of course, the telescope is primed to be able to take some information from that. There's also just the good old-fashioned way of just looking very far back, something like the Hubble Deep Fields, and that with the infrared sensitivity of the telescope, it can look further back on its own than the Hubble could. And so we're getting a census slowly of what the early galaxies, the number of early galaxies are out there. Now, a lot of us may have been very excited about 6 months ago or 8 months ago when it was reported that It was discovering galaxies in the very early universe that were a lot bigger than was expected. The problem with that is it was preliminary information, and in just the last couple of weeks, there has been a counter report saying that, oops, the original information was somewhat preliminary. We were looking at spectra based on photometric data rather than actual specific spectra taken with the spectrograph. And what they discovered is those really big galaxies they thought were occurring in the big early universe were actually a bit closer to us than they thought. That still we can still see much further back than we could with Hubble. It's just as though that excitement that the universe was very different than we expected is maybe a little bit less than it was a few months ago, unfortunately. So I just wanted to throw that out there that there has been some more recent research that suggests that some of that is just the differences between the measurement systems rather than necessarily the galaxies that were really big and really evolved being from the very early universe. Again, more pretty pictures, a lot of lensed galaxies in this particular image. There is a particular survey being done in the early science projects that look specifically at galaxy clusters that are thought or known to have a large amount of gravitational lensing. So we get a lot of pretty pictures that way, but you notice all the distorted galaxy images behind it. The beauty of this is, of course, when you get a lens like this, you get a little bit more light from the background objects. And of course, spectrographs need a lot of light in order to be able to operate properly because they spread the light out. And so with that kind of a thing, this is a great opportunity not only to get images, but to get some spectra of some of those objects, which give us a better sense of the distance and also how evolved they are. And again, this I think is a different field. They are doing a deep field much like they did with Hubble, I believe using the same field and several others as part of the experiment. I don't think this one, I think this one's looking is the survey that's looking specifically at lens galaxies, but it is, again, you can see that weird looking diffraction spike, but all these images, of course, are giving us a lot of scientific information along with being pretty pictures to put out for the public. Again, with the boxes looking at very distant galaxies that are of interest to scientists who are looking for, really things that were going on in the early universe. I love these images, so I put a lot of them up here. The one on the right, I believe, is looking with some visual or optical light, whereas the one on the left is looking at the mid and near infrared, just to give a comparison of what that would look like. And then here's Webb's first deep field. This is actually a somewhat older image. This is probably from the first 6 months of the releases, but again, some comparisons between what the Webb is able to do and what Hubble is able to do. What was interesting about this one is that galaxy on the right that is shown in both Webb and Hubble has a number of globular clusters in it. In the very early universe, unlike the modern universe, the globular clusters were still forming and still actively forming stars. So there's some real scientific interest in when that happened and how it happened. Whereas today they are very ancient and they don't have any star formation at all going on, if you're very little. And so this is an interesting part of sort of galactic archaeology to look back and see the time where the globular clusters of the early universe were forming pretty actively. Again, another deep image with a fair amount of lensing. Those swirly things are background galaxies, and the telescope is, of course, actively looking at that. And this is one that has a little bit of lensing, but again, looking at some of those background images. The pretty part is the foreground typically, but the part that they're scientifically interested is the little faint fuzzies that are way in the background because those are the earliest galaxies that we've seen in the universe, perhaps less than 1 billion years before or after the universe first formed. And of course, it's critical, and this is another star field they're looking at, again, with the images in the front.
So real quick, Stephen, just to chime in here with some scaling information because I was looking at this while you were talking. The field of view, which we didn't talk about, which Stephen didn't mention, is dependent on the instrument you're working on. The NIRCam has a field of view of about 2 arc minutes by 2 arc minutes, depending on the sensor. The MIRI instrument has a field of view of 1 arc minute by 2 arc minutes, and the spectrographs have, depending on which one, are slightly less than that. So you're comparing that to the moon. It's about your 30 arc minutes versus 2 arc minutes, and it's quite small.
All the these Hubble and James Webb both have very narrow fields of view. Is designed to see things in high resolution over a pretty small piece of sky. There are missions that, if anybody wants to take them on later, that are looking at wide field imaging and studies of the sky as well. But James Webb in general is not one of them. It's meant to look through a very narrow kind of straw to very deep, and also very high resolutions of nearby objects. A lot of these images, not these here, but the early ones I showed you, were probably composite images or mosaics that were assembled out of multiple images to create a full image of the objects. And of course, being with a larger mirror, you don't have to have as long an exposure, so you can take, it takes less time to build up a mosaic than it would be if you were with the Hubble or a smaller telescope. I think we all understand that principle from making mosaics ourselves of astro images.
So
This is again, go
as
ahead.
a as an example, the upcoming Nancy Grace Roman Space Telescope is one of the large field of view space surveying telescopes, which would be a whole separate presentation. But
Yes. In fact, that was one I may do in a few months. So that's another mission that hasn't been launched yet, but is coming up in the next couple of years. And again, this one I thought was good because it's got a lot of optical light in it, but it does show pretty clearly what the lensing looks like, which is that big streak sort of going down the middle. Not the blue one, the red one. The blue one is just a diffraction spike coming off a bright star. The red ones are background galaxies being shown to the back. So obviously, I love these images. And I wanted to close up with this particular picture. This is obviously not something taken by a telescope. This is an artist's conception of something that was announced this week, which has created a lot of interest, and which I have only done some very preliminary kind of scanning of what the story is. But this is a artist's conception of a super Earth that had its atmosphere explored by one of the infrared spectrographs on, I believe it was the mid-infrared spectrographs, MIRI on James Webb. And why this is significant is because there are telltale signs within the atmosphere of this thing that suggests there's possibly a water ocean. And one of the gases that was supposedly detected is also something that's a biosignature. So, not in any way, shape, or form definitive evidence that there's life there, but maybe a little clue that it's interesting. And that the reason I brought that up is we've seen a lot of pictures. We haven't talked a lot about the spectrographs on this thing. With real science, spectra is critical to doing real science. So, I mean, everybody loves the pictures, and they do have a lot of scientific merit. So it's not like they're irrelevant. But to do really, fine guidance science, you want to be able to take some spectra because the spectra will tell you more information about a specific object than a lot of the pictures will. Pictures worth 1,000 words, of course, but the spectra are important too. The reason this is important is because in the time since the mission was first conceived and the time it was launched, thousands of exoplanets have been discovered, including this one. And so one of the missions that maybe wasn't the top priority when it was first conceived, but is now a very top priority of this particular James Webb Space Telescope is to try and characterize the atmospheres of at least a few exoplanets. This exoplanet is a super Earth, mini Neptune, somewhere in between that. It's got about 8 times the mass of Earth. And it's making it smaller than Neptune, but much bigger than what we think of as anything terrestrial. But it may very well have a deep ocean on it. It does have an atmosphere of hydrogen, and so the imagery is kind of that. But again, more as an example of the kind of science that this can do, rather than necessarily anything like, oh wow, we found life. We did not find life by any measure with this, but it is kind of an illustration of the kind of cool science that this can do. That is very specific to the wavelengths that it's capable of, and its very large aperture for a space telescope. And just to throw out there, I think we're all pretty familiar as to why we put telescopes in space at this point. So I didn't go into a lot of that. Why I put an infrared telescope into space is because the Earth's atmosphere, especially the water, tends to block out a lot of the infrared spectrum from the ground, particularly the mid-infrared spectrum. And so it's important to have a space telescope with this kind of aperture to be able to do this kind of research because it's very difficult to do from the ground. Now, there was an instrument that was based on an airplane, Sophia, which has since been canceled. They could see further into the infrared within this. So it was doing a lot of cool, but not cool enough for NASA research. And that could see into the infrared as well, but not quite to the extent that this could. That got up into the low stratosphere, whereas this goes all the way out of the atmosphere, all the way away from moon and Earth, and it can get really cold in ways you can't do within the atmosphere and the like. So this was kind of just a way to close up with both current research and the fact that um, uh, we are in a really special place now that this thing is operating and fully functional. As I said, one of the exciting things about it is that it's actually operating as well as, and in some cases better than predicted. Which I never thought would have been possible even just a few years ago, but it is a magnificent instrument now that is working. If anybody want to do any follow-up reports later on, I may do a few of those too, because I think the science coming down from this thing has just been tremendous, along with the pretty pictures. And I wanted to finish up by acknowledging my mentor who is here tonight, Larry Lebowski, who is a very well-known infrared scientist in the planetary sciences. I'm so glad you're here. Thank you for being here tonight.
Thank you very much, Stephen.
Thank you, Stephen. Bravo.
And with that, oh, Larry.
Thanks, Stephen, for the talk.
And with that,
I should have asked if there are any questions.
Hey, Stephen P., I got one silly question. It's been bugging me ever since the thing was launched. It's kind of hard, you have the heat shield, and whenever you see the instrument, it's always, at a 90-degree angle, where I would think that it would be pointing 180 from it. Is that not correct? Is that just a misnomer?
I had the same question about it.
Okay.
And the best information I could find was that it can only see about 40% of the sky at a time. Whether it can look straight up from its perspective, I honestly don't know. But it typically it its ability to see the whole sky comes from being able to orbit around the whole sun as it goes around. It's not seeing, it can't point. See, obviously it can only point at 180 degrees, but how far it can see at any one time is about 40% of the sky.
Well, I get that as it goes around the sun, but what I'm curious is if they're able to tilt mechanically, not use rockets to move the whole spacecraft, but just the I guess just the telescope part is able to I don't know, hinge or whatever.
And if it can gimbal and all that.
Yeah.
It's just the whole telescope moves.
Yeah.
So the whole telescope moves, so they have to use the propulsion in order to align the whole telescope.
Reaction wheels. The reaction wheels on the bus can cause the thing to go like this and pivot it a little bit.
Okay.
Obviously, pivot it too far, or you would end up exposing it to sun, which would be terrible. But it's just like Hubble in that it doesn't use the thrusters very much. They want to conserve the as much as possible. It's using the reaction wheels to point the telescope and the
Okay.
so based little gyroscopes that do that. Which always had me a little nervous because the gyroscopes on Hubble ended up being replaced so many times. You had to wonder how long that's going to function. So far, they're working beautifully. So we'll keep our fingers crossed.
Very good.
But
Thank you.
how far the actual scope can tilt relative to the scope thing, I don't know. It sounds like it has to be gimbaled by the reaction wheels.
So This diagram I found earlier is anything to go off of. Give me 1 second to pull it back up.
I can stop share too.
Yeah. I'm waiting for this website to load. Then I will go here. My network decides to pull up. There it goes. Was it? Was it this one? I saw a diagram that had. I think it was one of yours, Stephen. Where it had lines coming off of the primary mirror showing like a potential field of view. So, I'm not quite sure. If you could go back to one of yours that had the mechanical diagram. I have to. I'll know. It's one of those. I'll know it when I see it, which image it was. If you can. You're also back on mute.
Okay, there's the mute again. And if I can get this to function, I know which ones you're talking about.
Maybe faster to cancel out of the presentation.
Go. So there's the mechanical diagrams. That's from the side. That's
This,
sort of,
no, not this one. Keep going.
I think that's the
Not
last
this
one.
No, there was another one. This one,
Okay.
I think. No, where was it? I may be mistaken, but I think it was like a 30-degree off of perpendicular. So like here with the J3 line is pointing straight up. So it had like, if I was reading the diagram correctly, it had another line that was pointing out about 40 degrees off of that.
This.
No, it was a mechanical drawing. Not quite sure if it was one that I had up in my Google history or something else.
That's all the mechanical diagrams I've got. Maybe this one?
Give me 1 second.
That's all the ones I put in there.
Where was it? I can't find it. I had it. I saw it, and it escapes me.
Okay.
But if it looked like it had like a cone of about 40 degrees on either side, directly above the scope, like in line with the heat shield, where that seemed like a dead zone that it couldn't see just from without tilting the whole scope as you needed to. So I don't think it can fully pivot itself to be pointing straight up and to where it's in line with the heat shield. Yeah, and the mechanical drawing, because it has that primary, if you look in the bottom right here, it has a primary stalk hiding out underneath it. So it would not be able to tilt just mechanically.
Yeah,
that whole
even
direction.
if so yeah. Pete, you're muted if you had another question.
No, that was it. I mean, it's something I'm going to take a look at too, but that makes sense that it does not hinge on the heat shield, or rather the whole spacecraft has to move. But of course, you don't want to move it such that the heat shield, doesn't block the sun anymore, because that sort of defeats the whole purpose. So it does have that limitation. But I understand being able to get, the sky pretty much in the solar plane pretty, over the space of a year, whereas trying to get it way above and way below the plane, that may be a little bit more difficult. Thank you.
Any other questions? I'm going to mute again and be done.
Cool. Thank you very much, Stephen. And with that, I'm going to go ahead and, if there's anyone else chiming in, I'm going to go ahead and end the recording.